Space is trying to kill you, not metaphorically, not eventually, immediately. The moment you step outside a pressurized environment without protection, space begins killing you in approximately 6 different ways simultaneously. No oxygen, extreme temperature, radiation, no pressure, micrometeorites, and the slow, relentless deterioration of your body in microgravity. The remarkable thing is not that space is dangerous. The remarkable thing is that we have figured out how to keep humans alive there anyway, for months at a time, in a tin can travelling at 28,000 kilometres per hour, with no shops, no hospitals, and no way home for 6 months. Let's go through the problems, one by one. Problem 1. Oxygen. You need it. Space has none. The International Space Station solves this through a process called electrolysis. Water is split into hydrogen and oxygen using electricity. The oxygen is pumped into the station's atmosphere, the hydrogen is vented overboard, but electrolysis requires water, and water on the ISS is not unlimited, which is why the station also runs a carbon dioxide removal assembly, a system that scrubs CO2 from the cabin air before it builds up to toxic levels, and a Sabatier reactor, which takes that CO2 and the hydrogen from electrolysis and combines them to produce water and methane. The water goes back into the electrolysis system. The methane gets vented. On top of this, the ISS carries solid fuel oxygen generators, sometimes called oxygen candles. In an emergency, these can be burned to release oxygen directly. They are literally fire that produces breathable air. The irony of burning things to make oxygen in a sealed spacecraft is not lost on the engineers who designed them. The oxygen system on the ISS is a closed loop of extraordinary complexity. Every breath the crew takes has been through a system that rivals anything in a chemical processing plant. And it mostly works. The word mostly is doing some work in that sentence. There have been incidents, but the crew is still breathing. Problem 2. Water. Here is a fact that astronauts on the ISS accept with remarkable equanimity. They drink recycled urine, not directly. It goes through an extensive purification system first. The water recovery system processes urine, sweat, and moisture from the cabin air through filtration, distillation, and chemical treatment. The result is water that is, by most measures, cleaner than tap water in many cities on Earth. The current system on the ISS recovers around 90% of all water aboard. A recent upgrade pushed that figure even higher. On a journey to Mars, which would take 7 to 9 months each way, water recycling becomes even more critical. You cannot carry enough water for a multi-year mission. You have to close the loop almost completely. The engineering challenge of life support in space is fundamentally the challenge of building a closed ecological system, one where almost nothing is wasted and almost everything is recycled. The ISS is the most sophisticated attempt at this humanity has ever built. It is imperfect, expensive to maintain, and occasionally alarming, but it works. Problem 3. Food. This is the one life support challenge that is least solved for long-duration missions. Currently, food for the ISS is supplied from Earth. Regular resupply missions bring fresh food, which astronauts describe as psychologically important beyond its nutritional value. The smell of fresh fruit in a spacecraft that has been sealed for months apparently has a remarkable effect on crew morale. But for a Mars mission, resupply from Earth is not an option. The communication delay alone, up to 24 minutes each way, makes real-time coordination impossible, and a resupply mission to Mars would take months. Growing food in space is the long-term answer. Experiments on the ISS have successfully grown lettuce, radishes, peppers, and other vegetables. The veggie system and the advanced plant habitat have demonstrated that plants can grow in microgravity under artificial light. But current space-grown food provides only a tiny fraction of a crew's caloric needs. Closing the food gap, growing enough calories in space to sustain a crew without resupply, remains one of the genuinely unsolved problems of long-duration spaceflight. For now, the food comes from Earth, which is one of the reasons a Mars mission is so much harder than it sounds. Problem 4. Temperature. Space is not cold. Space is complicated. In direct sunlight, the surface of a spacecraft can reach plus 120 degrees Celsius. In shadow, it can drop to minus 160 degrees. Sometimes both happen within minutes as the spacecraft passes in and out of the Earth's shadow. The ISS orbits the Earth approximately every 90 minutes. That means it experiences roughly 16 sunrises and sunsets per day. The thermal cycling this creates, constant swings between extreme heat and extreme cold, is one of the most demanding engineering challenges in spacecraft design. The thermal control system on the ISS uses ammonia as a coolant, circulating it through radiator panels on the outside of the station to dump excess heat into space. Inside the station, a separate water loop transfers heat from the crew and equipment to the ammonia system. The whole thing is carefully balanced to keep the interior at a comfortable 18 to 27 degrees Celsius, regardless of what's happening outside. When part of this system fails, as it has on several occasions, it becomes urgent very quickly. Ammonia leaks are particularly serious. Ammonia is toxic, and in space you cannot simply open a window. Problem 5. Radiation. This is the one that keeps mission planners up at night. On Earth, we are protected from the most harmful forms of space radiation by the planet's magnetic field and atmosphere. In low Earth orbit, where the ISS lives, the magnetic field still provides partial protection. But beyond low Earth orbit, on a journey to the Moon or Mars, that protection largely disappears. Space radiation comes in two main forms: galactic, cosmic rays, high-energy particles from outside the solar system that can penetrate almost any practical shielding, and solar particle events, intense bursts of radiation from solar flares and coronal mass ejections that can arrive with very little warning. Long-term exposure to space radiation significantly increases cancer risk. It may also cause neurological damage. Studies of astronauts who have flown long-duration missions have shown measurable changes in brain structure and cognitive function. The radiation dose for a Mars mission, estimated at around 0.66 sieverts for the journey alone, would exceed the lifetime exposure limit currently set for NASA astronauts. Shielding helps, but has severe limitations. The mass required to provide adequate shielding against galactic cosmic rays would make a spacecraft impractically heavy. The current strategy involves a combination of partial shielding, scheduling deep space missions during solar minimum, and hoping that pharmaceutical countermeasures under development, drugs that might repair radiation damage at the cellular level, prove effective in time. Radiation is not a solved problem, it is a managed risk. For a Mars mission, it becomes one of the most significant health challenges the crew would face. Problem 6. Pressure. Your blood would boil without it, not dramatically in the way films depict. More accurately, the gases dissolved in your blood and tissue, nitrogen, oxygen, carbon dioxide, would come out of solution and form bubbles. This is called ebulism. It is not survivable without immediate repressurization. A spacecraft or spacesuit has to maintain a breathable pressure at all times. The ISS maintains a pressure roughly equivalent to sea level on Earth. Spacesuits maintain a lower pressure, around a third of the sea level, which allows the suit to be flexible enough to work in, while still preventing ebulism. The transition between spacecraft and spacesuit pressure requires careful management. Astronauts preparing for spacewalks spend hours pre-breathing pure oxygen to flush nitrogen from their blood, preventing decompression sickness, the same condition that affects deep-sea divers who surface too quickly. The pressure systems on spacecraft are among the most safety-critical engineering challenges in human spaceflight. A breach is immediately life-threatening. Every seal, every hatch, every connection point is a potential failure. The engineering culture around pressure integrity in crewed spacecraft is meticulous for very good reason. Problem 7. Your body. And then there is the problem that no amount of engineering fully solves. What space does to the human body simply by being space. In microgravity, the human body begins to change. Fluid shifts toward the head, astronauts develop puffy faces, and what they describe as a permanent head cold sensation. The heart, no longer pumping blood upward against gravity, becomes more spherical and slightly less efficient. Vision changes occur, intracranial pressure increases, flattening the back of the eyeball, causing vision problems that in some astronauts persist after return to Earth. Bone density decreases at a rate of roughly 1 to 2% per month in the weight-bearing bones. Even with the 2 hours of mandatory daily exercise that ISS astronauts must complete, bone loss continues, just more slowly. After 6 months in space, astronauts typically need months of rehabilitation to fully recover. Muscle mass follows a similar trajectory. Skeletal muscles that are not used against gravity atrophy. The heart is a muscle. The muscles that keep you upright are muscles. In microgravity, they are not needed and they begin to disappear. 2 hours of exercise per day on a treadmill, cycle ergometer, and resistance device every day for the entire mission is not optional. It is what stands between a functioning crew and a crew that cannot walk when they return to Earth. For a Mars mission lasting 2 to 3 years, including the transit, surface operations, and return journey, the cumulative effect of microgravity on the human body is one of the most serious unanswered questions in human spaceflight. We know what 6 months does. We do not yet know what 2 years does. We have never done it. So, can we keep humans alive in space? Yes. The ISS has demonstrated that for missions up to 6 months and occasionally longer, the life support challenge is solved well enough for humans to function, work, and return to Earth in reasonable health. For a Mars mission, 7 to 9 months each way, months on the surface, radiation exposure beyond anything yet experienced, food systems that cannot rely on resupply, and body changes we have never studied at that duration. The honest answer is that we have solved the problems well enough for low Earth orbit. We have not yet solved them well enough for Mars. That gap between what we can do and what Mars requires is where the next chapter of human spaceflight needs to happen. The universe is not hospitable. It never promised to be. But we are, apparently, determined to go anyway. Next time, how fast can we actually travel in space? The gap between what we can do today and what the physics of the universe permits, and why the answer is both more exciting and more humbling than you might expect. Hit like if this gave you something to think about. Subscribe for a new video every Friday. See you then.